The application of this code is to determine the reflection and transmission of light based on the n value of a medium. This is a common optics problem. Our code asks the user to input an upper and lower bound for the second n value. The first n value is based on air. The code then plots the amplitude of reflection versus n and the transmittance versus n. The code also makes a third plot containing reflectance squared plus transmittance squared versus n.
The next section of this code determines the optimal N2 value for middle material in an anti-reflection glass structure. By optimizing it, we are ensuring the reflection coefficient R is 0. We do this with N1 equal to 1.0, N1 is air, and N2 values ranging from 1 to 3, the x-axis, and N3 ranging from 1.4 to 2.4. The circled points on the graph are the optimal points for the different N3 values. A plot of all the values is then created.
We begin the code by setting the n1 value equal to 1.0, which is the n value for air. The user is then queried for a high and low value for n2. A for loop is then created based on the low and high bound entered by the user, and it increases by 0.2. Gamma is then established by n1 minus n2 divided by n1 plus n2. A subplot is created. Gamma is plotted versus n2 and denoted by an asterisk. The plot is then titled and labeled. Next, transmittance is established by 2 times n plus 1 divided by n1 plus n2. A subplot is created, and the plot is then created of transmittance versus n2 denoted by a triangle. It is then titled and labeled. Another plot is created through the establishment of gamma squared plus transmittance squared. The third plot is created, and it is L versus N2, and it is then titled and labeled. And that is the end of the for loop.
Go.
First, we set the N1 value to be 1, so because our first material is air and the N value for air is 1. Then we set the N2 value to be 1 through 3, and these are different N values for the second material. Then we display N3 value, optimal value, because we're creating a table in the command window that you'll see later. Then we have 3 for loops, each of which do the same thing, but for different N3 values. Here we're doing it from 1.4 to 1.8. Inside the for loop, we set gamma to be N1 minus N2 squared divided by N3 divided by N1 plus N2 squared divided by N3. Then we set x equal to the square root of N1 times N3. X is the optimal value of N2 because it zeroes out the reflection. If you look above in the gamma equation, we're just taking the top of the equation, which is this part, and setting N1 equal to N2 squared divided by 3. Then we plot N2 versus gamma, and we set an O at x and 0, which is x0, 0 being the y value, which is the optimal value for N2. Then we display N3x in the command window, which is the N3 value and the optimal N2 value. Lastly, we label the graph with X label, Y label, and a title. Then we set the color of the graph, or of the plot for that N3 value, and this is what creates the rainbow effect of each N3 value plot. We have 3 for loops just so that the color can be changed and it looks like a rainbow. If you notice, the color is based off of N3.
It is now time to run our code. First, we enter an arbitrary low value of 1.0 and an arbitrary high value of 3.0. The graph for the first one is then created with the 3 plots as shown above, and the second plot is then created as well in a rainbow fashion and denotes where the anti-reflection is 0, which is what you want, and all the values are distributed in the display window. And that is what we've done with our knowledge gained at the University of Rochester using MatLab. Thank you. Bye.